equals to 200 volts. Is that clear, everybody? 200 volts. Make sense?
Yeah.
So within these 2 points. Here, I'm going to put 2 other plates. So these are like plates. Let's put it here. Plates. And these 2 things are also plates. You see what I mean? So 1 plate in here, I'm gonna put it, let me see, positive. So I'm gonna establish a potential difference here. And the other one is gonna be negative. You see what I mean? See what's happening, right? So 2 plates like this and 2 plates like this. I mean, 2 plates like this and 2 plates like this. You got it? Obviously, since this is positively charged and this is negatively charged, you know there would be an electric field this way, right? Right?
Yes, from high to low.
You know, from positive to negative, from high potential to low potential, but so there will be an electric field going down, a very uniform electric field. The plates are really close to one another. Or this is knowledge that you hopefully acquired from before.
That's not me.
But no, it's
Oh,
no,
I'm
it's
sorry. That's me. I put my laptop there. Then I'm gonna submit.
You're recording, right?
Yeah.
So if I say all this stuff now, you have proof. Anyway, I will say it anyway. So this electron that is like generated heat, I want it to go straight, like that. Are you guys, what?
It's a cameraman.
A cameraman? Oh, yeah.
It's a very intrusive recording.
So I want it to go straight. I'm gonna go straight, undeflected, but then it goes through this hole here. You got my idea there? So I want to know how fast is this electron when it gets to this point? How fast is it moving when it gets to that point? That's the first thing I want to know. You got my idea there? And the other thing I want to know is how strong is this electric field? Right? So that the electron moves undeflected. But I want to find the strength of the electric field, and I want to find the, what else?
The velocity of the
The speed of the electron when it gets to the other side.
speed.
Is that clear to everybody, guys? And I want you to think about it and see how you calculate it. The electron is going to be moving with a, speeding up, right? All right. Don't forget the potential difference between this point and this point is 200 volts. You know information, right? You know the mass of the electron. Anybody know the mass of the electron? If you do, you come here and teach. It's 9.11 times 10 to the negative 31 kilograms. The charge of the electron is negative. Everybody knows that by this age. Negative what?
6 point something.
1.6
You see
times 10 to the negative 19 coulomb. It's all right. It's all right. These are information that you already know. If you don't know, I'll give it to you. You don't need to memorize this. We got like cell phones these days. You know, some people. My daughter doesn't have one. Any questions about this? Any question about this? What would you use that phone? I pick it up from school, take it back to school. Right? Any questions?
In my times there were no
Well,
In my times there were no phones either.
I never got a phone till my son was born. And then I took credit. Any questions about this?
The software or the sun?
Huh?
The software or the sun?
How many ways?
I got a few.
You feel me?
No.
Oh, my God. Okay, go ahead. Yeah, my
Asking
wife
for
got the
the
best job
field
that you
after
do.
it gets out of
A
it.
job in which she can not use a cell phone. Go ahead.
You're asking for the field after it gets out of the plate.
What do you mean? Do you see the field in between the plates?
Okay.
How strong that field has to be so the electron move undeflected? Let's put it away. So the electron move on the, you know the meaning of that, right?
Yeah, without changing.
Straight line.
Yeah.
You see it? On how fast it gets to this point. So, believe it or not, this would be question 1, exam 3. You will deal with it. All this is previous knowledge. You should be able to do this. Is that clear to everybody? Got it? And the reason I put them on the board is because I'm going to set up an experiment too. And the first thing I have to do is to remember where I put the stuff. I'll put it in here.
Wait, do we know how far the plates are apart?
Doesn't matter. What do you need that for? So what are you doing now? What are you doing now? Brian, what are you doing now?
I'm recalling previous knowledge.
Don't recall, you don't recall anything. You're choosing a method.
Oh, yeah.
You got my point that you're gonna start like picking out like things unless you choose the method, right? If I give you like a bunch of tools, right? What are you gonna start? Oh, let me start picking tools, right? And then I decide what I'm gonna do with them. Is that the way it works?
No.
So what's the way it works? You decide what you're gonna do and then you pick the tool, right? So you're looking for how fast it is. Isn't that your objective?
Mm-hmm.
And then the tools. What are the tools that you have learned in this class?
The potential difference.
The potential difference. That's not a tool, that's a part of it.
Energy metal?
Haha! You see what I mean, right? This potential difference is useful for the energy method, true or false?
Mm-hmm.
Exactly. Or the force method. So what method are you going to use? Well, based on the information you have. Is that clear to everybody, guys? You see what I mean? So if you're looking for the speed at that point, and you know the potential difference between those 2 points, what method are you going to be choosing to calculate the speed? What is it? Energy method. Is that clear to everybody? This voltage, I can call it accelerating voltage. Is the voltage required to take the electron from 0 to whatever that speed is, right? And you're gonna use the energy method. Is that clear to everybody? In other words, there is some sort of energy that is going to become kinetic energy later on. You remember exam 1, you saw that 3 times in that exam. What's preparing you for exam 3? Go ahead, go ahead. Look at this piece of equipment that I transported from the Wilson campus to here. No, it's not stolen. It has a tag, I didn't steal the tag, it's still there. People know, the college know what it is. But since there was nobody there to use it, I moved it to this place. You get my point? So what I have in here, do you remember the lab you guys did?
Number 6, yes.
Charge to mass ratio of the electron. If you're taking it here, that's what I meant. This is a very fancy one. It's a beautiful one. This thing here, how much do you think you can pay for a light bulb?
$60.
This is $2,500 light bulb. It's a very expensive one. You have a whole like machinery inside.
Machine?
Huh? I don't know. You know, some sort of like a, you know, futuristic city. Now, if you look at it, you have like 2 plates and a gap in between. This is the gap. And this thing here is actually the other plate. You see it? And if you look at it, there is a hole there, right?
Yeah.
You see it? See the hole? That's where the electron is gonna come out. Straight out. You see the 2 plates? One plate and the other plate, so this is like pretty much that.
The black, down in there.
There's a hole, right? You see the hole? Do you see the hole? Who you listening to right now? What are you doing right now?
Exam 3 recitation.
Oh, exam 3 recitation during my class. Okay, that's a pretty good like, a priority when it comes to time. So, what is this? You didn't want this sitting outside, right? I'm gonna go there and tell him, come in and see your son over there. This is the education you give to that guy. I can promise you that if your mother is the way you be, you're gonna get beat up when you come back. Right? But now people don't believe in like, what do you call it, physical punishment? Getting shade the children?
Oh, yeah.
What do you think I got? You can agree that I come out all right, right? So you got it? So this is that. You got my point? Look at this one, it's like. So a little spanking, it doesn't have to, father, you do it with love. What happened?
I have a question, so.
Go ahead.
Why does the electric field, like, going downwards?
Because the electric field goes from positive to negative.
But the negative electron goes right.
Yeah, but what, that's nothing to do with that. That electric field is there just to make sure the electron goes straight. So that electric field is there because it's gonna have a force. In what direction is the force exerted by that electric field of that electron?
Down.
Down?
Oh.
Up. It's a negative charge.
Oh, I thought it was positive.
What? Oh, an electron is positive, even though it has a negative sign.
No.
Even though I put a negative sign.
I don't mean that.
You don't mean. I'll tell you what you mean. Anyway, so remember this, guys. The electric force is equal to the electric charge, whether positive or negative, times what? The electric field. Is that clear to everybody? You see what I mean? If the electric charge is positive, isn't that a nice way to put it? Then the electric force and the electric field go in the same direction. Is that clear to everybody? If the electric charge is negative, then the electric force goes in the opposite direction of the electric field. Is that clear to everybody? And that's true, because that's the relationship between electric force and electric field. Is that clear to everybody? My question to you is, as the electron moves through this region, how many forces are acting on it? How many forces are acting on it?
Actually, or?
How many hours do you sleep? How many hours do you sleep?
I forgot.
So I mean many hours?
I kind of forgot. I just went to bed and slept.
I slept 3. Go ahead.
So you got the electric field acting on it? You
The
got
electric field acting on it or the electric force?
the electric force, yeah.
In what direction is the electric force? So you see what he's doing, right?
Charge.
It's like picturing a 3-body diagram. Isn't that a nice thing to do? So this is the electron, right? That's the electron. How many forces are acting upon that electron?
Oh, you got the
Huh?
electric force.
4 forces. Name them. Let's see if you can name 2, 3.
I was looking at all the sides. I don't know.
Focus on the electron. How many forces are acting upon the electron?
Well, one, because
One. Which one?
the electric, the
Force. The electric force. In what direction is the electric force?
down.
Down.
You said right, but I didn't understand that.
I didn't say right. I
You
said
said,
it's up.
yeah.
The electron is negative, the electric field is going down, right? I told you that. So the electric force goes up. That's the electric force. Right? Which in size is equal to the charge, right? Let's put it like this, times the electric field. Is that right? Is that clear to everybody? What else is acting upon it?
Gravity, but it's too small.
But what? So, gravity take a holiday, you like persons, right? No, it doesn't. No. Gravity pulls the electron down because the electron has what?
Mass.
A mass. It's a small mass. It's small gravity, right? So gravity pulls this electron down. How strong is that force? How strong is that force?
Like 9.11 times.
So it is
10 to the
like,
negative.
yeah, exactly. It's like mg, am I right?
Oh, yeah.
You know that, right? And you have this value, right? Obviously, there is another force acting on it, which is the one accelerating the electron this way. And that's an electric force, but I don't have information about that force. You see what I mean? It's just like I don't know. I don't have information about that force. In fact, I'm not interested.
And then the other electrons keep them together.
¿De qué?
The other like protons keep them together to the coil.
What protons are you talking about?
Well, in order to shoot it, it has to come from somewhere. So that
Yeah,
place
it's
that
come
he said,
from, it's coming from, it's standing still
oh, it's standing still.
at that point, and then choo, you push this way.
Okay.
Got my idea? Is that clear to everybody? So, let's calculate the strength of the electric field so the electron moves undeflected. What is key about that, Roberto? The strength of the electric field so the electron moves undeflected. Do you calculate that? The electric field is gonna be mg. What is it?
I mean, it should be, if it's not moving down or moving up, and FE and MG has to be,
There you go, right? The net force has to be zero, at least in this direction, right? And that's what you do, right?
I just took what he said and gave it physics.
Don't defend. When you're right, people have to worry about, not you. Anyways, so what he's saying is, because it's moving undeflected, the sum of the forces along the y-axis, you gotta put like a y and an x, right? Isn't it? Have to be zero. Meaning that the electric force plus the force of gravity has to be zero. Do you agree with that? Right? Which means that the electric force has to be equal to the force of gravity. Isn't that nice?
But what if it's in the, like, if it's going right, then?
Okay, I'm talking about the y-axis. Let's focus about the y-axis first.
Okay.
Is that good?
I was
Oh.
if it was deflected, so.
Undeflected.
Like
It means it
straight line.
doesn't bend up or down.
Straight line.
Straight line.
Okay.
You know what I mean?
Sí,
Nothing is like.
No te preocupes, yo tampoco. Él lo explico.
What happened?
No te entendió el inglés.
Sin cambiar curso.
Sí, bro.
No tiene palabra.
Deflectado. No deflectado. I don't know, man. In a straight line. All right, so can you calculate the field there?
Yeah, because we know the chart.
mg divided by
No, 1.6
Q.
and 10.
So if you want to calculate this, you will say
What? Mass of the electron?
9.11 times 10 to the negative 31
30.
times 10. How about that? That is good, right?
Yeah.
Divided by
1.6.
1.6. No, don't put negative. All this is positive value because you are calculating values.
Yeah.
Times 10 to the negative 19, right?
Yeah.
And this is equal to, let's see. So 19, this is minus 30, right? Is that right?
Another 10.
Pero one.
Huh?
Pero one. Okay.
And then you got 30 minus 9 plus
Why is
19
it 30?
because this 10 here disappeared with that 31.
Oh, okay.
So you got, this is like 11, right? So you get double like 9.11 over 1.6 times 10 to the negative 11 newtons per coulomb. Is that right? So that's the way you do it. So what you take out of this? If the electron moves undeflected, then the force going up has to be equal to the force going down. In this case, I'm using gravity, right? It's kind of like, you know how difficult to create that such a weak electric field? It's very difficult. How you gonna do it? If anything that you use, it's gonna have a very like noisy area. You got my point, right? It's like people say that, oh, creating something very strong is difficult, right? Because the amount of energy is required. But something really weak is extremely difficult because the noise involving anything that you design is crazy. Is that clear to everybody? So that is not feasible, pretty much. In other words, using gravity to oppose the electric field is not feasible. And the reason is what you were saying before. The force of gravity of the electron is so weak, you know what I mean? That you want to use that for something, it's going to be like, what? Are you guys getting my idea? So now that you know how I did this, how about you actually use energy, the energy method, to calculate how fast is that electron when you get it out of that hole? Do that. How fast is the electron moving when it gets out of the hole?
0.
Zero? Who said that?
Me? Trevor, Davis.
This is your trip. Well, who cares anyways? Whoever said it, that's a pretty silly answer.
Yeah, if he's not moving.
How's it
he's
gonna
not
move,
moving.
man? It's 200 volts of energy that you give into that electron. You got my point, right? So use conservation of energy. That's the way you're gonna do it. You see what I mean?
Oh,
To calculate the speed of the electron at this point.
yeah.
You said when, as soon as it comes out, right? That should be 0, right?
No.
Oh, when over
Oh,
there.
he is this one. This is the question mark here. Of me, I told you that it's 0.
Yeah, I thought.
You know, that's, it's not moving. I assume it's not moving.
Maybe. Can we find the kinetic energy at 0?
You do what you have to.
200 volts.
8.38
3.38 watt chickens.
times 10 to the 25 meters times meters 6.
10 to the 25
Yeah.
meter per second. The speed of light is 3 times 10 to the.
Yeah, something like that.
You know, and nothing going on the speed of light. So you got a little calculation issue there. Maybe in a square root or something important.
I did it, square root.
So can you go to the board and do it, Roberto, please?
No,
Go to the board. Roberto, you're an artista. You are like a film person. You are like a celebrity. Like, I don't know. Big Diddy. So go out there.
Como que le falta
Sí, ¿no?
pintura a ti.
Huh?
Le falta un poquito de pintura a ti. Un poquito más.
but I got it once, so I don't know if it's okay.
So, ha! Brilliant. You see that? There you go. Keep going. Your issue is not physics. It's mathematics. Nobody gets less than an A in this class because of mathematics. You see what he did there, right, guys? He said, oh, the electron have electric potential energy, that's the E times V, and that converted into kinetic energy. And he skipped a bunch of steps, you know what I mean? Who cares? Everything is like, oh, you lose this, you gain that, the change of this, you will change of that, and blah, 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 you end up with that in amounts. Because I'm looking for the speed. What are you doing? What the heck is that? Oh, this is so funny. Get it back. You simplify things, then you complicate it to get back to this. So let me tell you what he did, you know what I mean, by he like reverse. So he says like, see, this is an electric force, right? Then you lose kinetic energy in the same amount, actually let's put it this way.
Potential.
You lose potential energy in the same amount you gain kinetic. That's what you said.
But I
Right?
forgot the triangle.
No, you don't have to. Because you're cleverer than that, you know what I mean? You actually went straight to the end. So let me show you, all right? Because this is like, yeah, this is, what you going? It's an statement, is that right? Got it? So what is this? Well, this is minus the potential energy at the end, right? Minus the potential energy at the beginning. Is that clear to everybody? Equals to the kinetic energy at the end minus the kinetic energy at the beginning. So notice that he was doing this at the moment, right? So what's the potential energy at the end? Well, you want to argue that it's like the charge of the electron, isn't it? Times the final potential. Is that right? Minus the charge of the electron times what? The initial potential. Is that clear to everybody? And this is equal to 1/2 mv squared minus 1/2 mv naught squared. True or false?
That was 0.
Huh?
Then that's 1 0.
So this is 0 because I told you, right? Now, what is the potential highest? Here or here? Huh? Here, right? Because the electron is going toward the high potential. You got my point? So, what's the potential here then?
0.
You can say 0. And here is 300. Do you remember that? So, this here, or 200, right? Is 200. This is 0. Look at what you have in here. The charge of an electron. I'm dealing with the scale. An electron is a negative particle.
Oh.
You got my point there?
Oh,
So when you
yeah.
put the negative in front of that E,
Cancel.
this goes away, and you end up with what? EV equals 1 and E squared. When you roll that down and say, oh my God, this guy's not only that is a great, what is your other actor, but he also can do mathematics and calculate the whole thing in his head. And you know why you were able to do that? Because your acting skills. You have to simplify. You have to simplify. You know what I mean? He said, I'm not gonna go through the whole process. I can go straight to that point. Boom. Is that clear to everybody? This is the amount I gain. This is the amount I lose. Is that clear to everybody? So you work with the amounts. Is that clear to everybody, guys? So he said in here what? Oh, let's put the numbers down, right? So that is like 1.6 times 10 to the negative 19. Is that right? Times 200. Is that right? Equals 1/2, 9.11 times 10 to the negative 31 times whatever I'm looking for. Is that right? So I use the energy method to calculate for the final speed. Roberto, can you do that for me?
I did it, mathematics wrong.
No, I'm pretty sure you were wrong with the scientific notation or whatever. It's supposed to be around 10 to the 6.
Oh, yeah. 592,
The speed at which the electron get out of the chamber is what?
592, 673, 8, 972.
Right.
Oh, that 40, that 3.
So this is a 3.9, right? That's it? That's the value? So it's like about 6 times 10 to the what? 1, 2, 3, 4, 5, 6, right? Meter per second. That's pretty fast, isn't it? Why that small potential difference can speed up that electron so much? Why? Let's say you learn some physics in this class. Or the physics. What?
Mass.
Oh my God. Because of the mass. You see the resistance to the force is so low that you can speed it up really fast. Good job, good job. Is this clear to you, guys? So all this is not from what we're gonna start covering today, all this is from before. Is that clear to everybody? Got it? So net force equals 0 will allow you to calculate stuff. Conservation of energy. I don't want to memorize anything. I wanted to understand what method I'm gonna use based on what? On the information given to you. Is that clear to everybody? Question number 1 on the exam is all about that. You're gonna choose the method based on the information given to you. Is this clear to everybody, guys? So be careful with this. Any questions? Questions on this? So let's speak about something extremely important in this planet and also people like take for granted. You know what I mean? Anybody know what I'm talking about?
Low.
The what? Go ahead.
Was it love?
Love?
That's what he said.
Love?
What?
I don't really grab it.
Like falling? No. I say in this planet. In this planet. Talking about physical property of this planet, most people take for granted. And it is the
Gravity?
magnetic field of the
Oh,
planet.
magnetic field.
You know what I mean? Nobody takes gravity for granted. Nobody jumps out of the building expecting that you're not gonna go down. You don't know that. Or I'm gonna jump out of the building because I'm falling in love. No, it's not gonna happen.
I mean, if you get a glider,
Maybe,
Huh?
if you get a glider, you can jump out.
maybe if you're depressed. What?
Why would you jump out of the building?
Glider.
A
I
glider?
don't know.
If you get a
No, you're
glider.
depressed. Get out of your depression by doing something useful.
If only were that easy.
It is easy. Believe me when I tell you. I've been depressed myself many times. Every time I got dumped by a girl, I was depressed. Until I got the other girl.
I mean, when you're busy, you don't have to be depressed.
You know, and why are you laughing? Isn't that true? So you focus on the future and you will never be depressed. Is that clear to everybody? Keep in mind you're going through things. Why? You have to. You got to get better, isn't it? Whatever happened to you, make it stronger. Isn't that like a phrase from somebody?
Dragon Ball.
Huh?
But the one I've heard is like do like the bald eagle.
Whatever doesn't kill you.
Makes you stronger. Yeah, it's Dragon Ball.
Who?
Dragon Ball.
I don't think that's true.
Who?
That's the Zenkai.
Who? Cannibal.
Dragon Ball is
Dragon
a
Ball.
cartoon.
Dragon Ball series. Do you think Dragon Ball can come out with that?
Yeah. They say it in the show.
Really?
My goodness. That phrase is from certain person from Greece. Okay? So I hope you people go a little bit beyond Dragon Balls. You know what I mean? You know, and Dragon Ball. This is so sad. The philosopher of this era are like Dragon Ball was the other one, Naruto or something. Well,
Demon Slayer.
huh?
Demon Slayer.
Who's that?
Oh, of course.
No, anymore. I remember Naruto. You know. Anyways, Naruto. Naruto has the name, right? Last name, right? Naruto. What?
Uzumaki.
That's the first name.
Huh?
Uzumaki. Uzumaki.
Naruto Uzumaki.
Yeah.
Look at this, how brave this guy is. Anyway, so let's speak about the gravitational field. What is the gravitational field? Everything started, you know, as everything that was written in a piece of paper, on this place in Greece called Magnesia. Have you heard about that?
No.
Magnesia? You never had like drunk like milk of magnesia?
Oh yeah.
You know what I'm talking about, right? When you have a stomachache, drink of magnesia. Anybody know why that is good? It's basic, you know what I mean, and brings down the acidity on your stomach. You know what I mean? And give you time for you to like recover. But anyways, what happened?
It tastes awful.
Well,
It's kinda minty.
it's called a medicine, isn't it? For a reason. We used to put them in our like armpits.
Hey.
Yeah, that's what deodorant is, because it's basic. The reason you get smelly down there is because it's
Acidic.
bacteria, which is acidic.
Because you're not seeing you in shower.
You know, you go to a certain age in which that things come out like that all the time. It's nothing to do with it. Nothing about taking showers. It's people, man. Anyways, let's go back to this. Let's go back to this. So, what I was talking about?
Magnesia.
Oh, Magnesia, this place in Greece, right? So this guy was a shepherd, right? A bunch of like goats. Isn't that what they have in Greece? Goats all over the place. So he had the cane, you know, the shepherd cane. And at the end, usually you put a piece of like iron, you know, so it doesn't splinter when you hit the rock. So he was walking with it, supposedly. All this is like written somewhere. And they got stuck and said, what the heck is going on? So he discovered at the time that there are some rocks that attract iron. You know what I mean? And magnesia, like magnets, you know. Like,
I don't know what magnesia is, but yes, I see that.
oh, magnesia is a place in Greece.
Okay, okay.
That's it. Don't worry about it. And this guy, I forgot his first name, but last name was from magnesia. Of magnesia. So, what is it? Here it is. Where I put my magnets. So look at this, guys. What is a magnet? Well, this is what you call a permanent magnet. It's just a piece of stone with certain physical properties and chemical properties. All right? And this guy, if you walk around with it and you let it be, it's going to be oriented. The string is unwinding now, so let's wait for it a little bit. And eventually it's going to point in certain preferential direction. Well, north. Well, what the heck is north?
Where the
Well,
South Pole is?
Yeah.
what?
It's where the South Pole is. It's where
North is where the South Pole is. That's kind of like counterintuitive.
Because it points towards the south, because north and south is opposite.
That's a good point. It was the one you're making there, as a matter of fact. So essentially, when you look at a magnet, so I'm going to tell you this because this is the way we want to start setting on our reference. Is that clear to everybody? When you look at a magnet, it's always have a north and a south. Is that clear to everybody? And you know this from forever. You know what I mean? That north and south attract each other, but same pole repel each other. You got my point there? Anybody knows that. Hello. Okay? But this thing, this north of the magnet, is pointing somewhere over there. So what should be somewhere over there in the direction of Hialeah? No,
Something magnetic.
a south. So he's right. You're right.
Because I've read the book.
Oh,
I'm not right.
Nice.
I just
So you got my point, right, guys? So this thing is pointing that way because there is a south pole over there. And notice that we have like positive, negative, and now we have north and south. Guess what came first?
Nothing.
The positive or negative or the north and south? The north and south. But understanding the magnetic property of matter came after, you know what I mean? The physics of magnetism came after the physics of electricity. Something interesting, isn't it? So anyway, so this is the point. There is so the key is if I walk around with this, I can actually follow a line, a magnetic field line, because you heard that field lines, like electric field lines, magnetic field line. Let me show you that. Let me show you what is my, oh, here it is. Here I have a bunch of oil, right? And a bunch of like iron fillings inside the oil. A bunch of pieces of iron. You see what I mean? You wanna shake it. You know, when you do the protein thingy that you use for whatever you waste your time with.
But you don't shake it, you blend it.
Eh?
You blend it.
No, don't you go around with the, my son had this thing that has like a little coil inside and goes like, what is disgusting?
Le quedan grumitos. Le quedan grumitos así,
Proteína comes tú.
¿Eh?
Proteína comes tú.
Triple X.
Porque te queda el grumo.
No sé, los lados sí, me quedan grupos. Yo prefiero hacerla por la batidora para que quede.
By the way, whoever is not understanding what you're talking about, there's
Don't.
nothing you miss.
You don't have to care.
It's actually better. Grumitos. What the heck is that? Grumitos, is that a word? Anyway, I know what it means, but so let me insert this magnet inside
Oh, they're gonna do like.
and see how these little things organize. Let me put it here, your super duper camera here.
Oh, it's cool.
So do you see what's going on?
Yes.
What do you see?
The magnetic, like, well,
They align, right? They create like lines. You see that? You're gonna get out of
Why does shaking it do that?
Oh, I shaked it before to spread the magnets around. The little iron field. You see that? You see the lines? Especially the lines.
Oh, it's like a magnetic field. Like a vector field.
Looks like a vector field,
Yeah,
yes,
vector
which is
field.
coming from a magnet. So how do you call that field? Magnetic field? Like magnetic field?
Vectorial field.
You see the lines? Especially at the end. You see
Eso
the-
es increíble.
You see that? So, yes.
Sí, eso lo explica
There is
en cálculo
such a thing as a magnet. You see the lines, right?
El vectorial field, ¿eso cómo se llama?
See the lines?
Magnetic field.
Are you guys getting my idea? If you actually look at this closely, you're gonna see that the lines far away from the magnet are like more sparse. Showing what? The closer to the magnet, the stronger the field. Makes sense. Oh, I forgot about you. You're listening. What are you listening to right now? Who are you listening to? Any? What's the name of that?
Nah, he doesn't have video face.
Huh?
He doesn't like a new
What's it? Eminem. Isn't that like a two little things for you? That you eat? No, but Eminem.
R&B.
The 9 Mile guy. Eminem. You know. Yeah, Eminem. The rappers, that guy.
R&B.
Eminem.
Rock.
That's not.
Huh?
Look, I have two swivels in here. Are you looking at that? So if I put the magnet on the swivels, like this one here, and the other one here, you see they are north and north? I know, they will rearrange until that. You see the magnetic field lines that go like a star and end, like that? So you understand this, right? So yeah, the planet Earth. Anybody know the name of this?
Compass?
It's a compass. Do you know what this is useful for?
Navigation.
Yeah. Why this is useful?
Because it points north.
Do you know who invented this?
Someone
compass.
that invented.
Chinese.
Oh, Chinese.
So it's pointing north. You look at it. It's hard to see it, but it's pointing north, like around that way. You got my point? Why? This is just a magnet. The same as the one that I have with the string there. So there is a magnetic field of planet Earth that looks like that one that you saw there. So you look at planet Earth. All right? You can look at planet Earth as something like this. If you put a compass here, the compass is going to point north and south. You know, Canada is north. Argentina is south. You understand that? Is India north or south? India is in north or south?
From here.
No. No.
From where? Where the origin?
From
From the
where?
equator, equator.
Anyways, you got my point, right? So if this is true, that means here you have a magnetic south, isn't it? And here you got a magnetic north. True or false? Because the needle is pointing that way. So this needle points on the direction of the magnetic field. Is this clear to everybody? So you can argue that this planet is something like this. And that's what you saw. Is that clear to everybody? So there is a line here, so when you put a compass here, it's gonna point to the geographic north. Is that clear to everybody?
I'm still kind of confused.
Why are you confused? Geographic north versus magnetic north. What you read in the book is that over here, you have a magnetic south. And over here, you have a magnetic north. But the geographic north is here, and the geographic south is here. So you have to make that distinction.
So basically, geographically, we're pointing north, but
Magnetically.
like
Magnetically, it's
south.
pointing south,
Yeah.
yes, that's the meaning of that. So that's the whole point. In here, you have some sort of vortex. And I guess you know that those vortex create this beautiful display of light called the Northern Lights. We're gonna speak about that later on. Is that clear? What?
Do the southern lights?
Aurora Borealis, that's the other way you call it. You know what I mean?
Why does it curve like
Northern
that?
Lights, or like Brother Bear, remember the movie?
Why does it curve
Do
like that?
southern lights exist?
What was that?
Do southern lights exist?
Yes, of course they do.
Why does it?
Let me ask you a question. Are penguins bipolar?
No.
What is that?
No, only on the north.
They live on the south.
The penguins on the south?
Yeah, they are.
I know that
There's penguins in New
bears
York.
don't live together or something like that.
Penguins?
They live everywhere.
Yeah, there's penguins in Madagascar.
But-
Huh?
There's penguins in Madagascar.
Well, but that's in the south.
Yeah, no, that's what I mean, like.
There are
there's
penguins in
penguins
Peru. In Peru, I
Exactly.
saw them with my own. I have pictures in my cell phone. The penguins there like dancing. Like the other animal, the what do you call that? The seal, like lion.
What
Something.
is penguins being bipolar?
Excuse me?
What is penguins being bipolar mean?
They get depressed.
I mean, maybe.
Penguins are not bipolar because they are originally from Antarctica, so they live in the southern hemisphere. This is so funny because for a long, I watched this movie called like Happy Feet. All my life, I thought penguins live wherever there was ice, penguins are there. You know what I mean? And then I watched like Happy Feet, right? Which made me believe that penguins are in the North Pole. Because the thing happened in New York, right? Why would you go all the way here to, collect the penguin? You go over here. You know what I mean? Do you see penguins being eaten by polar bears?
No, only seals and.
Why you don't see penguins eaten by polar bears?
Because the polar bears are.
Polar bears are really far from that. You know what I mean? So,
Maybe they ate all of them.
huh?
Maybe they ate all of them.
Maybe, but we don't have like proof of that. So, penguins are not bipolar. They are pretty well, one thing. Okay. Go ahead.
Why does the magnetic field curve? Why doesn't it just point straight to it instead?
Because you have a whole sphere there. And it has to follow in here, you see what I mean? It comes here, and it goes like this. You know why?
Don't know.
So North Pole, South Pole, right? So if you have a north in here and a south in here, how will you draw the magnetic field line between these 2 points? Okay, right here, and this is the reason why you care. Right here, you will have this. Right? Here, you have this, and then as you start going up, because of the edge effect, they're gonna start bending. See what I mean? That's why it curves. You got it? But if you look at a magnet, and this is important what I'm about to say now. If you look at a magnet, and this is the north, and this is the south of that magnet, right? How we draw the field lines? From north, right, to south, right? Like this. And you saw that. It's not I'm making this up. You saw it with your own eyes. So these are the direction of the magnetic field line. But what happened inside the magnet?
Same thing.
Because this is the whole magnet, isn't it? What happened you cut a magnet in half?
You get 2 magnets.
You get 2 magnets with 2 north poles and 2 south poles. In fact, I remember I was teaching a class when I was a high school teacher, right? And I have a magnet there. And there was this girl sitting there. I was, behind the desk and stuff like that. And I got a hammer. And I got, bang, and broke the magnet. At the very instant I hit that girl went, You know what happened in Cuba when you get somebody one eye gone,
Oh, bro.
you have to marry that girl. Well, of course, it's an age difference, I wouldn't be able to do that. So I'm screwed in America if I do that. But you know what happened? One of those small flies went in her eye at the very exact moment I hit the hammer. For like 2 seconds, I was like, oh, my life is ended. I want to be reporter and stuff like that. You know what I mean? But it was like that. Oh, you go, and it was a little fly. Those, no wasasa, I don't know how you call it. But anyway, I broke that thing to show that you have 2 magnets, pretty much. Got it? So, you see what's happening here, right, guys? So inside the magnet, what happens is actually this.
The opposite.
No, it's like they form, except H. You got my point, right? So magnetic field lines don't have a beginning or an end. Go ahead.
Does the moon has a magnetic field?
What?
Does the moon has a magnetic field?
The moon, okay, good question, good question. No, it doesn't. Neither Mercury. You see what I mean?
But it's not iron, right?
No, that's not the point. You know Mars used to have a magnetic field? Mars has a very thin atmosphere at the moment. You know what I mean? And a lot of people think it's like global warming. Remember, the emission and all this type of stuff? And cars, the atmosphere, rivers dry now, the caps melting. So what happened to Mars? I've never seen anybody driving over there. Oh, they have rovers now, but they don't use
Over
caps.
time, it just loses magnetism or something?
Exactly. Mars core, first of all, Mars is a little bit smaller. Mars is almost the size of the moon. You know what I mean? And the core was hot at a certain time, but it cooled down, cooled down, cooled down. Eventually, what happened? There is not enough hot core inside to create the magnetic field. There is not enough molten iron moving around, an electron, to create the magnetic field. And weak magnetic field means high energy particle from the sun go inside. This is a very simplistic way of explaining it, and pretty much evaporate the atmosphere. You see what I mean? But you look at Mars, there are like rivers and valleys and stuff like that. You got my point there?
I don't get it
Because the magnetic field protects the planet from the radiation coming from the sun.
so like over time, like everything will just go away.
The Earth, yeah, eventually the core will melt. We are like due to flip the north and the south, right? That happens on the Earth every certain amount of years. Because remember, you have all this molten lava inside the center. So the core, around it is liquid. You see what I mean? All that movement creates the magnetic field here. It's a very important thing. You know what I mean? There are a lot of people studying, you know, the effect of, you know, what they used to be called global warming, they're changing now to climate change, so you can put whatever you want there. So, based on the fluctuations on the magnetic field of the Earth. You see what I mean? And this is a good point. It's like, yeah, you know, you want to say like carbon, you know, emissions or whatever, fine. But how about you look at other factors? You know what I mean?
Can you create magnetism?
Can you create a magnet?
Not create a magnet, but
Yes,
like.
yes, you can. Yes, you can. Can you create a magnetic field? Yes, you can. That's gonna be question 2 and 3 on the exam. Anyways, questions about this, guys? So everybody's clear about this? All right. So you have the idea. The symbol we use for magnetic field in this class is a B. Is magnetic field a vector?
Yes.
Yes.
Yes, it is. Is that simple enough, guys?
Yes.
You see it? So let's speak now about, and this is going to be the topic of the first question of the exam, and the second question, and the third question, and if I have a fourth one, I put that in. The magnetic force. The magnetic force. Got my idea there? In order for me to do that, I'm going to prepare this piece of equipment I have in here. So let me remind you what I have in here. In this very expensive light bulb, I have a filament at the end that I'm going to heat up to produce what? Electrons. Exactly, everybody. So I'm going to send a current to that wire, it's going to get hot, and it's going to produce electrons. You won't be able to see the electrons, you know, you will never see the electrons, but you're going to be able to see a little light there. That means that portion of the wire is hot. Exactly, and the electrons are like jumping out. Then I'm going to accelerate those electrons through 200 volts. You got my point there? You got it? Then I'm going to set a magnetic field in this business. You got it? And see what happens to this. So I'm going to put it back. Carefully. Carefully. This thing is like probably like 30 years old. But we use it like once a year. Not my iPhone. What do you pay tuition for? Anyway. So I'm going to turn this on, and I'm going to start connecting this. Okay, well, the wire, get there. So this thing in here is a high voltage power supply. You know what I mean? If you connect this point to this point, you can take it all the way to 500 volts. You got my idea? And that is the voltage I'm going to use as what I call the accelerating voltage. Is that clear to everybody? The 200 volts that you saw there before. Got it? So I'm going to have the positive. It says high voltage here, danger, blah, 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 blah. And in here it says handful coil. Over here it says like I don't know what, and deflecting plate, electrodes, heater, blah, 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 blah. Here it says measuring voltage, so that you put something there. What the heck is it? Accelerating voltage, hello. Deflect plate, voltmeter, volt. Here it is, here it is. It says in here, it says it there. From 150 to 200. And this part in here, this part here, it says on the top, electron gun. So you're producing electron and shooting the electron that way. That's what you guys did before. Is that clear, everybody? So I'm going to accelerate the electrons. Let me get another wire. Notice that the wires I'm using here, one is black and the other one is red. Why is that? Because direction matters. Is that clear to everybody? So if I flip that, then the potential difference is the opposite of what it was before. Is that clear to everybody? So I have that. Okay. Now notice that the other part of the electron gun, the filament, doesn't have any color. Why? Because the only thing you need to run a current. Direction doesn't matter. Is that clear to everybody? So heater, that's what you call it, heater, because you're gonna heat up the wire. So I don't know what I'm gonna put it here, maybe. Let me bring this down. Keep in mind that a safety mechanism, whenever you're dealing with equipment, is bring all the knobs down, just in case. You got it? Any questions about this? Now, another thing I'm going to do is I'm going to run a current through this wire. You see it? And for that, I'm gonna use this super duper power supply. And it says in here, Helmholtz coil. This is 2 coils with certain amount of turns, you know what I mean? Separated by certain distance. And the purpose of that, you're going to see. When you ask that question, it's like, can you create the magnetic field? I'll show you how you can do it. Have you heard about this thing called electromagnet? There you go. There you go. So, what was that?
You created with electricity.
So that's what you call an electromagnet. It's a magnet that is not natural. You know what I mean? It's not a rock. What are you doing? Oh, what? Oh yeah, what are you doing here? Okay. I need to bring the windows down. For those of you that still don't understand, look at how much we invest in your education.
That's what that tuition goes to.
Esa no era la placa.
And my salary.
No, para abajo, abajo.
Hold on, that's technology, you know. I got a degree in physics, not in technology. Down we go.
Oh.
Wow.
Ah, no, vamos.
You know how long it took me to learn this? Like 3 years. All right. So I'm going to turn off the light. And I need to turn on this. I wonder how to do it.
That was like,
How do you turn on this?
That right, Mark?
Roberto,
With this?
me desaparezco.
Break. You see? Somebody's going in the class. I can do this one too, right?
Yeah.
No, this one has a button on the other side. The last time this one worked, what este was? What?
58 minutes.
All right. So I'm going to heat up the filament. Oh, actually you can see it already, right? No, actually you see nothing. You're seeing the red button. So I'm going to heat up the filament by I forgot what it was. This one here. Let's see.
Isn't it a lab?
What was that?
Isn't it just like our lab?
Yeah, but this one is a special one.
We didn't get a lamp, we got like a helium thing.
Oh.
What the heck is the filament? Why is it not heating up? Seriously.
I'm gonna see if it blows up.
What?
Ahora no conectamos, pues no.
Gonna blow up. It's also gonna blow up.
Me desaparezco.
Don't tell me that this actually died on me. You're gonna do that to me, man. You teach a class.
30 minutes.
Okay, this is not working.
The light bulb.
What was that?
Light bulb is not connected.
The light bulb is connected, of course connected. Question there. It's right there. Let me- What was that?
Problemas en el paraíso.
Problemas en el paraíso. Might be. So nothing? Okay, I'll try again. Let me put him in another power supply. Maybe the power supply is not working. Do me a favor, you be using, at least for one, you like, and bring me one of those, power supplies over there. Do you know what's happening? No, I use depress, whatever that means. Depress, right? That's what we call it. Isn't that depress an exercise or something? Thank you, sir. I hope you didn't bring the only one that is broken.
I bring 6.
All right, so let me put this in here.
la abrigo nada más.
¿Ah?
De verdad.
Ese pequeño negro ahí es-
Vamos a ver, vamos a ver. Cookie.
Pero no se me diga la
Aha! Do you see that? Shiny. You see that? Let me show it to you. You see the light?
Yeah.
You see it?
a little bit.
What do you want to see?
I was expecting something like a.
Oh, no. This is the filament that is hot, nothing else. It's not everybody. Electrons are being produced at that point, and those electrons have the speed of what? Zero, almost. Is that everybody? So what I'm going to do now, I'm going to speed up those electrons. Oh, actually, they're moving up already. You notice that? Why? Because I have a voltage. Let me change this to the voltage. You see it? I have 102 volts. You got my idea there? So notice that I have a beam of electrons pointing that guy. So you don't have to cover that. Come back here. Come back here. You see, the dream of every professor. I'm shooting the electrons to you guys. It's not killing students. It's actually giving you electrons so you study better. You know what I mean? More energy to study. You see that? So you see the beam of electrons going over there.
Uh-huh.
Make sense? So you saw it, right? It's not I'm making it up.
It's like a
Can I,
lightsaber.
can I ask a question that might be dumb? Is the light bulb
You need
an
to-
insulator?
Huh?
Is the light bulb an insulator?
The level.
The glass.
So why doesn't it like shatter the glass if it's shooting electrons?
It's actually doing.
It's still.
No, but it's like the glass is, those electrons are like, you know, the mass of the electrons are like 9 times 10 to the negative 31.
So
You have a
it's
point, so you just go through that glass like if nothing happened to them. You know what I mean?
And it's coming out, right?
It's going out, now I'm shooting him, you see what I mean? Put the head there, man, you might get better. You got an idea there? That's what is happening. Obviously, the only part that you see is inside the bulb, because the bulb is filled with a gas, which is called helium. Is that clear to everybody? When the electron goes through the helium gas, it excites the levels, and then it releases green. So you are not seeing the electron, you are seeing the trace left of the electron. Got my idea there? So let me slow down the electrons. I'm gonna slow down the electron with this.
Is the gas the
Do you notice that you see nothing, right? Because there is not enough energy to move the electron and get him out of that hole. Is that clear to everybody? Are you guys getting my point there? Okay. Now, turn on the light, please. Click. Somebody. And I'm gonna use this compass. You see what I mean? Which at the moment is pointing north. Right? I'm gonna get it close to here and see what happens to it. You see what happens?
I didn't see because your hand is in the way. I'm guessing that it pointed towards
Okay,
it.
you didn't see anything because nothing is happening.
Yeah, she said that.
Oh.
You got my idea, right? It's pointing north, pointing north, pointing north. All right? Let me put this. Oh, you see I have this on my hand? You go. So put it close to you when you do the whole. So let's put this on top of this. And it's pointing north. What happened? So what I'm going to do is I'm going to run a current through those wires. Got it? I need to actually do something because I want to be falling over there. So let me get up. Where did I put it? Anybody put it? Inside that Sharky that you have behind you. Give me a tape, blue tape that's there. Throw it to me if you can.
Yo lo tengo.
Like this. So, let me,
No, así. Claro, se va a quedar así.
huh?
Así más hombre si lo digo así. I can, so I'm more man if I throw like this than this.
Oh, that makes you more.
Yeah.
Claro, tira así el
It requires for me the next day.
Así de simple. Yo lo tengo.
I don't know. There used to be higher standards in the past.
Demasiado.
That's a me.
Sí, ve. Ahí.
Society has changed so much. You know? So I'm gonna run a current to this wire. All right, this thing is pointing. Hello, point north, like over there. Okay. So watch. I'm gonna run a current to the wire. What current I'm gonna use? This one. Watch. Again. Now I have this control. This is a control, another control. So watch. What is that telling you?
That this coil is positive and this one is negative.
South is not that way.
This is magnetism. There's no positive and negative.
So this is not.
So there is a magnetic field going in what direction? Inside those coils. In what direction is the magnetic field going? Okay, inside the coils. In what direction is the magnetic field going?
Oh, this one.
Towards you. Towards you. Do you agree with me on that?
Ajá. Ese sí.
Here we go. Inside the coil,
¿Dónde? Aquí.
where the magnet is.
No.
Ah, okay.
In between the coils.
In between, okay. In between.
So you got my point there, right, guys? So essentially what's happening, how do you draw a magnetic field like that? How do you draw a magnetic field like that? So these are the coils. This is what you're seeing, right? Right? How do you draw a magnetic field like that?
Dots.
A bunch of dots. Do you agree with me on that? You see it? That's what it is. And then you put a little circle in here. So now inside the coil, you have a magnetic field going out of the board. Let me say it. Out of the board. Is that okay? So, question to you. What's the direction of the magnetic field? Out of the board. Is that clear to everybody? So if I give you an image with a bunch of dots, I'm telling you that the magnetic field is coming out of the board. Is that clear to everybody? It's simple as that. You know that, right? From like vectors in 3 dimensions?
Can you?
You know what I mean?
change that?
If this is a vector, okay, and that's the magnetic field, and you're looking at this, you're going to see the feathers of that arrow. Is that clear to everybody? You look from here, you're going to see the tip of the arrow. Is that clear to everybody? So let me flip the magnetic field. How can I flip the magnetic field? Well, I'll tell you, I can run the current in the opposite direction. Is that clear to everybody?
Oh.
So I'm going to flip it, flip it, flip it, flip it, if. And there you go. You got my point there, right? You see the magnet pointing that way? So what is the meaning of that? Well, this is the coil, and inside the coil, the magnetic field is going into the board. Is that clear to everybody? Into the board. Simple enough? Questions about this?
Why? What's affecting the direction of?
Well, that is sources of magnetic field. I created the magnetic field by the use of an electric current going through the wire. Do you hear that, Trevor? That's it. So this is for later. These are sources of magnetic field. Those of you that are taking the lab in here, we did that already. Remember that? We got a coil, we run a current through it, and we tested the magnetic field inside that coil. The lab that we did, which is called like magnetic field and sling. So that's pretty much, but it's a different one. The beautiful thing about this arrangement is that the magnetic field inside the coil is pretty uniform. If you actually measure it, you're gonna see that it takes the same value everywhere, which is kind of cool. Now look at this. Actually, I'm gonna leave that one there. And I'm gonna put another over here. The problem is that that one might be affecting it, but go ahead.
Yeah, that's right.
This is gonna be a painful problem.
What do you mean painful problem? It's already posted, man.
I know.
Look, I'm gonna flip this magnet, right? You see that?
Agárralo abajo.
See what he does.
Oh, no.
You see what he does? In what direction he's pointing?
Wait, the top one?
That way, which is what you were saying. So this is like, you got my point there? So essentially, if you look at the coil from the side, that's the coil, right? The magnetic field is gonna be circles like this. Are you guys getting my idea here? Now, if you compare the strength of the magnetic field outside with the strength of the magnetic field inside,
Inside is stronger.
a lot stronger.
Yeah, because it moved
Like,
easier.
you
than-
saw it, right? You see how
had
strong
to,
it is
you had to
inside?
give it like an impulse to start moving.
Exactly.
back.
You got my point, right, guys? So outside is almost like no magnetic field. You can actually, if you compare the two, you say outside is zero. It's so weak. You know what I mean? But inside is pretty strong. Let me flip it. Let me flip it. Look at that one. It's still spinning because it went so fast that it got so much momentum that it takes a while to stop. So you see that, right, guys? You understand that? So, but that's for later. That's going to be question number 2, question number 3 of the next exam. Right? The question number 2 is sources of magnetic field, especially this thing called like Ampere's law, very easy thing. All right, and the last one would be the application of this into a circuit. In other words, I will introduce the concept of an inductor. Are you guys getting my idea?
Can you say the question?
It's already posted. It's posted. Go look at it.
I wanna write it. Okay.
Okay. Question 1,
Okay.
magnetic force. Question 2,
Okay, wait.
Ampere's law.
You record.
Yeah, that is true.
Question 3, it's recording itself. That's the nice thing about it. And question 3 is RL circuits. Got it? Is that good? So let's now get that beam of electrons and expose it to a magnetic field that is going out of the board. Is that clear to everybody? So who wants to turn on the lights? Maria. Maria, you're working upstairs. Vamos a ver.
Pero quiero decir, un texto atrás, ¿verdad? Antes que se caiga, sacarlo de rango. De manera que, como voy sacando de rango, vaya-
So let me send the electrons. So I'm going to accelerate the electrons over there by giving an accelerating voltage. Is that right? So let me start increasing this. You see, 101, 119, tan, 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 tan. So I'm gonna make what? 200 volts. Is that clear? What's the speed of these electrons, Roberto?
592.
There you go. It's about 6 times 10 to the 6, right? You got my point? Why? Because it's based on this entirely. The rest is a bunch of constants, true holes. And you see the electron, but notice what happened to those electrons. Now they are being forced to move in a circle. You see my point?
What? What did you increase?
I increase nothing. Now the electrons are going through a magnetic field. If there is no magnetic field,
Straight line.
the electrons keep on going, the same way they were moving before. Is that clear to everybody, guys? You got it? Is there gravity acting on those electrons?
Yes.
Yes, it is. Is that gravity able to bend the electrons down? Not at all. Is that clear to everybody?
Wait, so in this case, there's no electric field.
No magnetic
Oh,
field.
magnetic. Sorry, magnetic.
No magnetic field, yes.
But there is an electric field, and the electrons.
Yeah, the
strong
electric field is
enough
to
not
speed out
move.
the electrons. That's it.
Okay.
Are you guys getting my idea? So look at this. I'm going to shoot the electrons this way. So I'm shooting Lawrence. Get out of the way, Lawrence. I'm joking.
No, sure.
All right. So I'm shooting the electrons that way. Is that clear to everybody? I'm going to set the magnetic field. Again. Do you see anything?
You traced it.
No, there is a magnetic field there. But the electrons are not being bent by the magnetic field. The electrons are not being forced to move in a circle by the magnetic field.
Because the magnetic field goes with the coil.
Well, I don't know. The magnetic field is going that way, exactly as everybody, and the electrons are moving that way.
Yeah.
So why they don't move in a circle? Let me ask you before I do that. Why they move in a circle?
Perpendicular? It's perpendicular.
But why they move in a circle? Go ahead.
Because the magnetic field is so strong that they
Yeah.
are forced to follow.
He mentioned the word force. The only way you can move a particle in a circle is if you have a force acting on it. True or false? Remember Newton's first law? An object in motion will remain in motion. An object at rest will stay at rest unless compelled to change by means of an external force. Is that clear to everybody? So, is there magnetic force in here?
Not
In
right
this
now.
case? No. Is that clear to everybody?
So it's like we said, they're parallel.
Well, if the electron move in the same direction as the field, the magnetic field is what? The magnetic force is what?
Positive?
Zero.
Oh, zero.
Zero. Do you agree with me on that? Look, let me give a little angle. Just a little bit. Do you notice that now the magnetic field is able to bend?
Oh.
You see that? In a spiral. A beautiful thing. You got my point there, right? Now, if the magnetic field is perpendicular to the velocity of the electrons, the motion would be a beautiful what?
Circle.
Circle. Is this clear to everybody?
Yes, sir.
If the angle is not 90 degrees,
Spiral.
it's in a spiral. You got my point? Obviously, in this class, because of the nature of this class, remember? What's the nature of this class?
Physics, watered down.
It's introductory.
Hold that. Okay, you're gonna have always a situation in which the electrons will move perpendicular to the magnetic field. Is this clear to everybody? See what I'm going to do now. I'm going to speed up the electrons. Are you listening to me? I'm going to speed up the electrons. How can I speed up the electrons?
Increasing the voltage.
By increasing the accelerating voltage. Remember that? So I'm gonna move this to 300 and see what happened to the radius of that circle.
It gets thinner.
More current, so it gets thicker.
Don't think of current. Think of field. The field is the same, but the electrons are moving faster. You got my point there? Are you guys getting my idea here? Let me ask you a question. How do you call the force able to rotate an object? I mean, to make an object go in a circle. How do you call? It's not a force. The force here is magnetic. But how do you call it? No.
Centrifugal.
Centripetal. Remember that? So these electrons that are moving in a circle have what? A centripetal acceleration.
You mean,
Excuse me?
isn't it centrifugal?
Centripetal. Centrifugal is something else that have nothing to do with it. Are you guys getting my idea here, guys? Now, let me actually increase the strength of the magnetic field. By, what can I do to increase the strength of the magnetic field?
More current.
More current. You heard that, Trevor? So watch. What happened to the radius of the circle?
It gets smaller.
So why the radius of the circle gets smaller? Because you have a stronger force. So you can bend it faster. Is that clear to everybody, guys? You see it? Questions about this? Questions about this?
That's beautiful.
You got it? Go ahead.
When it's going out, it doesn't get excited.
Okay, let's put it this way. What I show you is that if I point the electrons this way, in this moment the field is going that way too, right? Isn't it? What's the magnetic force? Zero.
Zero.
You got it? You might argue, oh, how about they are speeding up?
Yeah.
Well, they can, because when this is the case, they move in a circle. So a centripetal force will not be able to speed up or slow down anything. The only thing it can do is what?
Rotate.
Change the direction. Change the direction.
Change direction.
You got my point there, right? So the electrons are moving in the same direction as the what? As the field, right? No force. Let me flip the field. How about that? You got it? So I'm gonna flip the field. In other words, the field at this moment is going that way, right? Isn't that what we have before? Right? You don't believe me? I can put the
Turn
mic
around,
there.
turn around the light bulb, no?
Oh, you can do this. No, I don't want to turn on the light bulb. I can actually. So you see the field's going that way. You notice? The red one is going there. So what I'm going to do, I'm gonna switch the wires so the field goes into the board. Is that right? So I'm gonna get this out of here and put this over here.
No. It wasn't that one.
Nope, my bad. It's supposed to be this one.
No. No, it's the ones in the machine.
Oh, that's true. This is like the accelerating voltage. My bad. My bad. It is this one, right?
No,
This one, right?
so what's in the machine?
So I'm gonna flip it. Estos. Yeah, but I can do it too. Okay, yeah, you're right. Let's do it this way.
You're not connecting with that one. Está conectado con el de arriba.
No, look. You see?
Okay.
So I'm gonna flip this, so I'm flipping the field. What's the force? The same as before. So whenever the electron moves in the same direction or in the opposite direction as the field, the magnetic force is zero. It seems that the magnetic force is proportional to the strength of the field, right? Right? And the magnetic field is proportional to what? To how fast they move. Is that clear to everybody? All right, so here we go. Well, you saw it, right, guys? It's not what I told you.
We got a relationship.
So what are the relationship I'm establishing here? So this is what you guys did in the lab, pretty much. But the lab is like a piece of equipment, strong enough you can operate it, and you don't need to do what to change that. And you prove this, right? So essentially what is happening here is this magnetic force, I'm going to use the letter F, put an arrow on top and a B here. You got my point?
Luego lo está separando.
So there is two things here. Is the charge of the particle. What particle are we dealing with here?
Electrons.
Electrons. There is the velocity of the particles, isn't it? And what else?
The electric field.
The strength of the magnetic field. Is this clear to everybody? Something you saw here is what? Whenever V, right, was equal to B, do you understand what I'm referring to with this? Direction. Exactly, everybody. Whenever the direction of the movement of the electrons was equal to the
Magnetic field.
direction of the magnetic field, or whenever this was equal to minus this, which is I did it, I showed you that. What was the magnetic force in that case?
Zero.
The magnetic force was it. Is that clear to everybody? Whenever B was perpendicular to B, like in the case when I have the field like that on this way, the electron moves in a circle. True or false? So, can somebody tell me what is can somebody come here to the board and draw the velocity of the electron at that point?
No entendí. No escuché.
Can you come to the board and draw the velocity of the electron, the velocity vector of the electron at that point?
It's going.
The velocity vector. The velocity at that point. I don't know what's the meaning of at that point means. Point. At that point. What the heck is that?
Yeah.
Velocity.
Ah.
Draw the point again. Draw the velocity. Okay, you're missing something here. What he's missing is that the velocity vector always goes tangential to the path. Is that clear to everybody? Since the electrons are moving counterclockwise, you better draw something like this. You see it? That's the velocity. True or false? True or false? Right? You want to draw the velocity here, how you do it? Right? My question to you is how the size of this vector compared to the size of this one?
The same?
Same size. How do you know that? It's a perfect circle. Are you guys getting my idea here, right? Got the point? So the electrons don't speed up or slow down. The only thing they do is what?
Change direction.
Change direction. Can somebody tell me what's the force acting on that particle so it moves in that perfect circle? What's the direction of the force?
Into the circle?
Into the circle?
Into the board.
Into the board?
Oh, out of the board.
Out of the board? The magnetic force?
Yeah. Oh.
Oh, down.
Thank you. What's the direction of the force?
Oh, yeah.
I said it.
What's the direction of the force exerted by the, whatever that is, on the keys?
Into the finger?
Towards the finger,
As I said it, towards the circle.
towards the center. Centripetal, sounds familiar? Centripetal? Right? So the magnetic force is centripetal. How you draw a centripetal force?
Also, that's why it's called centrifugal, because it's going to.
Centripetal, not centrifugal. So look, this is the direction of the magnetic force at that point. This is the direction of the magnetic force at that point. I know because that's the only force creating this effect. Is that clear to everybody? Yeah, you might argue it's gravity, but gravity, you would already is like, who cares about gravity? Is that clear to everybody? So you understand this point here, guys. So notice that this is what? 90 degrees. Is that clear to everybody? You can argue, observe this, that the strength of the magnetic force is equal to the mass of the particle, in this case an electron, right? Times the speed of the particle squared divided by the radius of the circle the particle is describing. Centripetal acceleration, remember that? Physics 1?
Why do you say you can argue? You make it sound like
That's
it's.
colloquial.
Okay.
It's like the way of saying things. It's the same as you can say, you know. You can defend your thesis. So, any question about this, guys? So, whenever there is a magnetic force acting upon a particle that is moving, that magnetic force is going to be what? Centripetal. Is that clear to everybody? That's the reason why it wasn't a spiral, or it was nothing. Is that clear to everybody? I have two vectors at play here. V and B. You see what I mean? Let me refresh your mind a little bit about cross product.
That's the one that is the.
Let me start with dot product. Let's say you have vector A, dot vector B. Is that clear to everybody? You probably remember that it's like A, cosine of the angle between A and B, times B, right? Remember that?
Mm-hmm.
The projection of A onto B, you mean. So if this angle is 90 degrees, what would this be?
0.
0. Is that clear to everybody? So this cannot be dot product, then it's what?
Cross product.
Cross product. So this is what you get. In other words, the magnetic force is somehow related to the cross product between the velocity and the field. Does that make sense to you?
I get it, but not really, because you just said, oh, because that doesn't work, we're just gonna go to that.
But there's only two choices.
Okay.
You know what I mean? You got two choices, and one doesn't work, then the other choice. You're multiplying two vectors, right?
And you said that when they're perpendicular is.
And you saw all that in here. You got my point there? In fact, if the angle between V and B, and B is 90 degrees, you got that beautiful perfect circle. You got my point there? Which is what's gonna happen in this class. Now, observe this, observe this. Something that I cannot test you here because I only have electrons available here is the charge, the effect of the charge in this business. Is that clear to everybody? So, the greater the charge, the stronger the magnetic force. And this thing you have in here on the board right now is how do you calculate the magnetic force between a particle, not between, the magnetic force exerted by a magnetic field on a particle of charge Q moving with velocity V. This is the way you do it. Is that clear to everybody? If you remember a little bit about cross product, you might remember that the magnitude of the magnetic force using this is equal to Q, just value, no sign, isn't it? V, B, what else?
Side.
There you go. Of the angle between the two. Are you guys getting my idea here? In this class, that angle will be what?
1.
The angle will be 90, so what would this be? I know what you mean. You mean that this is gonna be 1. Exactly, everybody? So you will be able to find the magnetic force by multiplying the amount of charge, I'm insisting on that because the sign doesn't go there, times the speed of the particle, times the strength of the magnetic field on that particle. Is that simple enough? So since that particle is going to be moving with the speed v, then you can say that q v b. You see my perfect English? q v b and q. So b for us is the same as b. So, but in here I have to make a distinction because it's v b. I don't know. I guess that's the way. So this is equal to what? M v squared. Oh.
Beautiful.
Is this clear to everybody? Questions about this? Questions about this? So hereby I present to you the magnetic force. And I did a whole experiment. I show you what is a magnetic field, the way you have it there, how that equipment is set up, and so on and so forth. Go ahead.
I have a question.
Go ahead.
I've been playing with these magnets.
I wonder why you're playing with the magnets and nobody lent you.
Oh, yeah, you gave it to me, he wanted it, so I gave it to him.
Ah, yeah.
So
Who
something
gave
like-
it to you? It's a question, dude.
I'm trying to find out what is the south of this magnet because it connects from both sides. It doesn't repel like
Because
this
it's not a
too.
magnet, it's a piece of iron.
Oh, really?
Yes. So it's not a strong magnetic field to separate, you know what I mean?
Oh, very.
Anyway, does anybody have any questions? Does anybody have any questions? So, with this information, you should be able, are you listening to me?
I'm listening, I just got tired of it hanging over.
Of
my
listening?
head.
So, what I'm trying to tell you is that question number 1 on the recitation, with the information you have at this moment, you should be able to do it. Do you understand?
All right.
Question number 1, the recitation. You got it? So what I'm gonna do as soon as I come up next class, what is gonna be my opening statement on next class?
Do the problem.
I'm gonna solve question number 1, the recitation. Come late at your own peril.
Thank you, Billy.
Got it, guys?
What if you can do it yourself and?
If you don't come, then you don't need me. Just show me that when I give you an exam. Everything is gonna be all right. Everybody sign up the name of the sign-in sheet?
No,
You want shining sheet?
no, I don't see.
Yes, there was a sign-in sheet, which I passed around. Yes. And I put it in front of you and you kept it. That's like my order.
¿Desde cuándo está eso?
Ah,
¿Desde cuándo?
Hoy,
since the beginning of the class. Go ahead.
hoy,
¿Por qué?
no sé, pero hoy la primera vez que yo escuché eso.
No,
Entonces yo le bloquearon por
hay otro link. Un link no es el access person, es otro poco de
If you get it close enough, it's gonna stick, right? But if you take it out of range, this move when it's in the stick. So how fast you have to move it? So this follows and just shoots itself. That's what I'm saying, like how fast do you have to like constantly keep it so it just keeps moving. Like this, so this is what it means. Because I think my reaction is not fast enough. You see? So I'm not fast enough to take out
The
range.
thing is, it's a constant force, so then the velocity will be,
I can react.
it's a constant force acting upon it, so it's a constant acceleration. It's not a constant velocity, so you have to continue accelerating more and more and more
Oh,
to keep it.
Never mind. I was just trying to like just play with it. And they just follow each other. That's it.